Dear student, welcome to my channel. Topic of this video is Diffie-Hellman key exchange algorithm. Now let us start. One of the main problem of symmetric key encryption is to require a secure and reliable channel for the shared key exchange, because in symmetric key encryption the same key is used at the encryption and the decryption side. The Diffie-Hellman key exchange offers a way in which public channel can be used to create a confidential shared key. In practice, the shared encryption key relies on complex operations such as modular exponent, primitive roots, and discrete logarithmic problem. Each party selects a private key and exchange a computed public value. Using the other party's public value and their own private key, both compute the same shared secret. So these two lines are nothing but the procedure of Diffie-Hellman key exchange. So these steps will be clear when we are solving the problem. It forms the basis of many modern cryptographic systems and enable secure communication without sharing the private key directly. We will use asymmetric encryption to exchange the secret key between the users. It is conceived by Ralph Merkle and named after the Whitfield Diffie and Martin Hellman in 1976. It is the first practical example of public key exchange in cryptography. It is used in various security protocols like TLS, Transport Layer Security, IP Security, Secure Socket Header, and Pretty Good Privacies and other algorithms. Now we will see the Diffie-Hellman exchange algorithm. This algorithm is very easy. We require to select the two global public elements, that is P is any prime number, and we require to find out the primitive root of P, which is nothing but G. I will explain how we calculate the primitive root of P. Then we require to select the private values for each user. They are private, they are not exchanged. Now here, by using their private values, they are generating the key. For example, user A generates the key, user B generates the key, and their keys are public and they are transferring to each other. Exchange the user keys from both sides. Now the calculation of the secret key by A. So here the A user will use own private key and the shared public key of B, and here B use its own private key and the shared public key of A to calculate the key, and the key generated is same on both sides. The same secret key is derived by both users using their own private keys. Now here the public parameters are nothing but prime number P, primitive root of P, A public and B public. Now we will see what is meant by primitive root of prime number P. It is a number G where G is less than P and follows the criteria, that is G raised to I mod P gives a unique result for every G. Now we see the example. Now here P is equal to 7. So primitive root for that set is nothing but G equal to from 1 to 6. Now for example, we have to check for each number. Now we will see the number 3 and 5. So when we take the 3, then we require to do this operation, that is 3 raised to I mod P, and here I will goes from 1 to P minus 1. So 3 raised to 1 to 3 raised to 6, and here we check the another number 5 raised to 1 to 5 raised to 6. So when we do operation, that is 3 raised to 1 mod 7, 3 raised to 2 mod 7, in this way continuously, and on the right hand side we can clearly see that this G has a capacity to generate all the numbers for P. So all numbers from 1 to P minus 1 get generated by using this G I raised to I mod P operation. Similarly for 5 raised to 1 to 5 raised to 6, and 1, 2, 3, 4, 5, 6, all number gets generated. Now actually we require to try for all numbers. Now first we will start with 1. When we take 1, all the remainders are 1. When we take 2, then at that time we can see that all numbers not get generated. So this is not primitive root. With 3 generated, 4 not generated, 5 generated, and 6 is also not generated. So primitive root for prime number P 7 is nothing but 3 and 5. Now we will see how to solve the problem. P is a prime number. We require to find out the generator from the P. X is a private key of the user A, Y is a private key of the user B, and K is nothing but the shared secret key which is calculated by both sides, and both are same. So first A calculates the public key. A public is equal to G raised to X mod P. Then B calculates the public key by using its own secret key, that is nothing but Y, that is G raised to Y mod P. Now here they are exchanging. For example, A public will goes to the B and B public will goes to the A. Now A calculates B raised to X. This is nothing but the B public raised to X mod P, and B calculates A raised to public raised to Y mod P. So here you can observe that whenever A and B are calculating the keys at their sides, they are always using the exponent as their private keys and which are not shared. In this way, the K gets generated same on both sides, and after that they can start the symmetric communication over the insecure channel. Now this is the operation. For example, A calculates, that is nothing but B public raised to X mod P. B public is nothing but G raised to Y mod P, and the same why the key gets same generated on both sides, because this operation takes place. This is very easy to understand. Just it is replaced by A public is nothing but G raised to X mod P, and here we can see that the same key generated at the both sides. Now we'll see the problem. Alice and Bob use Diffie Hellman secret key exchange algorithm with common prime P equal to 19. Primitive root is G. Alice secret key is phi and Bob's secret key is Y. Here X equal to 5, Y equal to 6. Find out the common key shared between the Alice and Bob. So first, given is all this value. X is private key, B is private key, which is less than P. Now here first we calculate A raised to public, which is nothing but G raised to X mod P. Now here P is 19 and G, that is primitive root, is nothing but 10. Therefore 10 raised to 5 mod 19 is equal to 3. Then B public is equal to G raised to Y mod P. Now this is nothing but 19, that is nothing but P. This is primitive root G 10, and this is nothing but the secret key of Bob, that is nothing but 6. So 10 raised to 5 mod 19 is equal to 3, and 10 raised to 6 mod 19 equal to 11. Now A public gets 3 and B public gets 11. Now these two parties A and B, they are exchange that keys to each other. Now we'll see how this operation we can easily compute using the square and multiply algorithm. Now I already published the video on square and multiply algorithm. When the exponent is large, this operation is very efficient, but it is, as this exponent is less, we can directly do that 100 square, that is 10 square mod 19. After that we can do that operation also. So here for u, so we represent for u as a binary. So binary for u is 101. We take from MSB to LSB. The operation is equal to z equal to z square mod n. Initially z we take as a 1 square mod 19 1. Z equal to z into base is nothing but 10. So 1 into 10. Now z becomes 1 into 10 mod 19 10. Now 0. When 0 is there, only we are performing one operation, that is nothing but square. And when the bit is 1, we are doing both operations, square and multiply. Now again 1. So z updated 5 square mod 19 is 6, and then z is equal to z into base is 10. So 10 and 6 into 10 mod 19 is equal to 3. So A public gets generated 3. So here I am explaining on the fast track because I have already published the video, so better you watch the video, so it is very easy for the understand. So 6 is nothing but 110. Initially z is 1 square mod 19 1. As it is 1, so we are doing the next operation, that is nothing but multiply. So 1 into 10, base is nothing but 10. See, this is the base. So 10 mod 19 10. Then next 10 square mod 19 5. Then 5 into 10 mod 19 12. Square mod 19 is equal to 12 square mod 19 is equal to 11. Now Alice calculates the shared key using the Bob's public key. Now K is equal to, now Bob will share the public key, that is B public, and here the Alice will calculate as B public raised to X mod P, that is nothing but K equal to 11 raised to X mod P. Now the private key of the Alice is 5, so 11 raised to 5 mod 19 is equal to 7. So again this operation is explained with the help of square and multiply algorithm. So 5 is nothing but 101, and here initially z is equal to 1, and all operations are calculated So when 0 is there, only we are doing square operation, but when 1 is there, we are doing both operations, square and multiply. So in this way we calculate. And similarly B will calculate A's public key, because here A and B first generate the public keys by using their secret, then they exchange. Then here B will calculate based on A raised to public raised to y mod P. So in this way they gets calculated. Now Bob will calculate A raised to public raised to y mod P, which is equal to 3 raised to y mod P. Now B's secret is nothing but 6, so 3 raised to 6 mod 19, 7. So here we can again apply the square and multiply algorithm, because when we use this algorithm, at that time the chances of errors are very less, because the procedure is very systematic and every time we require to do with a very small operations. Now see the next example, P23, G7, X3, Y6. So first these are all values are given. So first we calculate G raised to X mod P. P is 23, G, that is primitive root, is 7, 3, 7 raised to 3 mod 23, 21. G raised to Y mod P, that is nothing but the 7, that is primitive root, and this is nothing but P, 7 raised to 6 mod 23, which is equal to 4. Now they are exchanging with each other, and after that this A raised to public raised to Y, it will calculate K, and here A will calculate B raised to public raised to X mod P. So here we can see the operation. A public is equal to, now this operation is only explain again with the square and multiply algorithm. In the next slide we will calculate the K. So 3, 1, 1, we will do the all operation, 6, and we can see that some of the operation gets repeated. For example, see this operation, so here we can directly use the result. So in this way A public and B public gets calculated. Now we exchange with each other to calculate the K value. So B public raised to X mod P, 4 raised to X mod 23, which is 18, and 21 raised to 6 mod P, 18. So same key is shared between the two users. You can calculate this operation directly because number is very small, but when exponent is large, at that time better way to follow this algorithm. Even we follow this algorithm even for small number, the procedure become very modular and systematic. Now see the third problem. P is 11, G is 7, 3 and 6 get shared. Sorry, 3 and 6 are nothing but their private keys respectively. So these all values are given. So there is no need to explain. You can just watch. This is P, this is G, private key of A, private key of B. This is explained with the square and multiply algorithm. Now we exchange each other to calculate the K's value. Now here the operation is very simple, but if you want you can use the square and multiply algorithm. 2 raised to 6 mod 11 is very easy. So you can try for this problem. I guess here I have to check whether G equal to is prime rod, or you can check also by using a simple, if you are doing the programming you can use a simple for loop, or otherwise if you are doing the calculation you can check. So these are the references for video. Thank you.